Hi everyone, my name is Timur Yunusov and I have my co-speaker today, Aleksei Stennikov. We are the part of Payment Village organizers and our presentation today is POSWorld, should you be afraid of hands-on payment devices. We are going to talk about vulnerabilities that we found in two biggest point-of-sale vendors, how these vulnerabilities can be used, what attacks can be done, and many more. So for the purpose of this presentation, we call it the POSWorld, and in this POSWorld we have many different entities. But at the top of everything we have PCI, Payment Card Industry Council, which is responsible for maintaining PCI DSS or Data Security Standard, which explains how card data should be transmitted, stored, and so on, and protected against hackers. Then we have two biggest card brands, Visa and MasterCard. We have different variety of point-of-sale vendors, but the biggest and one we are talking about today are Verifone and Ingenico. Then you have obviously issuing and acquiring banks who are responsible for handling and sending money between accounts. You have merchants, shops who are selling goods to customers, which are the cardholders essentially, and we obviously have hackers here. So in our threat model, hackers can be either malicious customers or malicious merchants. So if you look at the payment process, you can see that malicious customers, for example, can modify point of sale for the purpose of collecting card data and selling it on the dark market. But if you'll be able to infect the terminal, if you are, for example, a malicious merchant, you will be able to affect the further process of the card transmitting and, for example, send unauthorized data to the issuing acquiring bank, so unauthorized transactions will be accepted. We're going to talk about this a little bit later. PCI says that there are certain rules about how card data should be handled, and they have few documents about point of sale terminals or PIN pads. So we have PCI PTS or PIN transaction security document. We have PED security requirements, which is PIN entry device requirements, and there are hundreds of pages, different questionnaire requirements, so on and so on. But briefly speaking, we are talking about few major things. So first is obviously do not store, send or process sensitive data, cardholder data without encryption. Things like PIN codes, track 2 data from magnetic stripe, or CVV codes from the backside of the card. Next, specifically to terminals, each terminal should be tamper protected, so protected against any opening, drilling, trying to extract any data, and whenever this was detected, terminal should act, so it should delete all sensitive data such as encryption keys, payment apps, and so on and so on. It actually not specified what exact data should be deleted, and in the end your device should indicate that it was compromised. So essentially turn itself into a brick so it won't be functional anymore. And in our world we have obviously hackers, because stealing payment data is a very lucrative business for them. But before we'll start talking about the history of hacking, I want to show the difference between two very similar definitions. So we have POS terminals and POS systems, and sometimes they might be mixed. So when we're talking about POS terminals, definitions are POS, PIN pad, PDQ, or just a terminal, where POS systems can be called cash registers as well. So what's the difference? If you're talking about the big machine with Windows on board, with the keyboard, barcode reader, where the cashier puts money in, you are talking about POS system. When on the other hand, the device where you enter your card and enter your PIN code is POS terminal or PIN pad. And obviously they are not the same. If you read about how hundreds, thousands of devices were hacked and card data was stolen, you probably will be reading about malware which was installed on POS systems. And the same if you will Google POS hacking or try to find any videos or different white papers, you highly likely will meet information about compromising and hacking POS systems and installing malware there. But obviously there were hacks of point-of-sale terminals in the past as well. So researchers from University of Cambridge ran Tetris on a device back in the day, infected the POS terminal, which was quite good. Then we had researchers from SR Labs who found vulnerabilities in one of the most popular model in Europe. We ourselves made some research in the past, so in 2017 we had a presentation about vulnerabilities in mobile point-of-sale systems. But now I will pass the microphone to Aleksei, and he will talk about how these devices look like, what vulnerabilities they have, and how hackers can attack them.
Hi there, thanks Timur. The first step in order to make your own evil and weaponized creature is understanding its weaknesses and internals. Basically, every terminal hides from you a bunch of legacy code, technologies and strange approaches. And it's great to understand the whole technology stack starting from hardware. In this talk, we don't have enough time to describe point-of-sale hardware in details, but we have already published this information on DEFCON and Payment Village. More details you will find on the Village YouTube channel. I'd recommend you to pay attention to this channel because it also contains other useful information. And now we are going to shed light on software components. It's time to weaponize your POS terminal. We should keep in mind that we are going to break into secured, well-protected and certified devices. When the vendor goes to PCI certification, he should satisfy PCI rules and fill a form like previously discussed one. Suddenly, the successful certification itself don't guarantee that device is completely unhackable. The first creature to weaponize is Ingenico pinpad. Let it be slowpoke. Our findings affect the whole product line of such terminals. There is basically no difference, is it portable or countertop. They all built using the same hardware and use the same Telium2 operating system. This is just an example of this series, but I'm sure this kind of terminals is well known for all of you. It is expectable that all the communications to the bank servers are encrypted, but there is an alternative way to get into it: the maintenance tools and special modes. The main software for server sections called LLT. It is usually used for application and operating system logs collection, firmware upload, and operating system and application updates. To connect a pinpad to LLT software, you should boot the device with special key combination. What does this mode hide? First of all, it uses a very strange way to establish connection to the device. The terminal itself is recognized as a virtual COM port when USB cable is connected. LLT software brings up PPP connection over this virtual COM port. When this connection is established, the pinpad initiates connection to PC6000 TCP port and waits a response from LLT software. Usually the LLT software sends a command to pinpad to open FTP server in order to get access to some part of device file system. The interesting thing here is the code credentials for every step. Also, no one has an ability to change these passwords because they are part of operating system binaries. The protocol on 6000 TCP port used to open FTP server is called NTPT3. It is completely insecure with absolutely no authentication and other integrity control mechanisms. By exploiting this vulnerability and having direct connection to terminals USB, an attacker gains access to internal FTP servers. It also has some undocumented commands. LLT is allowed to read only file system, the directories, host and swap. One vulnerability allows reading any files whose absolute path is less than 17 characters long. It allows an attacker to obtain cryptographic keys and manipulate traffic between point of sale and acquirer. Also, some extra functions of this protocol are buggy too. The third interesting finding in this chain is trace protocol with no authentication and encryption. Trace mode is intended to monitor performance of banking application during development for post-debugging and assist developers with debug capabilities. By using this protocol and having direct connection to the terminal's interfaces, for example USB, an attacker gains access to terminal operating system and application internals via trace command line interface. Anyone has access to this command line interface just using the config file magic and the trace tool from software development kit. Example of trace tool output is the following. This command line interface has help commands in order to get description for every available command. But a research wouldn't be complete without a bunch of non-declared commands. As you may see, it exposes to attacker additional function to get hardware and software status and some additional debug capabilities. As a result, this semi-debug mode allows full control of the pin pad. The exposed commands allow to allocate and deallocate memory, display the contents of all files of the terminal internal file system including encryption keys, and to suspend, resume and terminate processes and threads. The example attack scenario is classical. Allocate the memory for malicious code, then write malicious code to allocated memory. Suspend and modify non-important tasks in order to point to our code, and then just resume suspended task. Finally, we have code execution on any Telium-based Ingenico terminals. Is it a good result for such research? Definitely yes. Is it a good news for their customers? Probably no. But anyway, we have another riches in our research. The next riche is well-known Verifone terminals. This is an example of their VX series terminal VX520. Let's figure out what can we do with this creature. The entire VX product line uses VerixV operating system. It is proprietary one as in previous example. Executables for Verix operating system has .out extension with their own binary format and should be signed in order to be executed on the pin pad. The default password for this type of pin pad discussed many times, but no one changes it. You can find the same password even in ancient Zone XL pin pads from 18th of previous century. To enter the service mode, you have to press F2 and F4 keys during the boot of pin pad and enter the password. This mode allows to modify internal variables and obtain technical information about the exact pin pad model and install updates. Example of such variable is Go variable. It should contain an executable file name for autorun when terminal is turned on. The VerixV based terminal has a file system divided to multiple drives. Some of them mentioned in documentation, but some of them are used internally by the vendor and are contained RAM drive, some partition on NAND flash drive, drives related to boot block, and additional file systems. The drives mentioned below the list are marked as reserved and written by the Verix operating system during production. This is a very interesting thing because we haven't found any useful information related to these drives in any sources. In the reason, we paid attention to them and found some gifts from developers. We all know that all executable files should have their digital signatures, but a drive T is another case. Its contents can be modified, and all the binaries you can find there are trusted by operating system by default. You can modify the configuration file on file system menu in order to execute any of .out files from drive T. The most interesting of findings on the internal and undocumented file system is the shell binary. Probably once upon a time this was used for recovery and debugging, but now it's just legacy piece of executable code. To execute it, we should modify go and r variable, as you can see on this slide. The results of this modification is the following. Instead of merchant application, the pin pad started the kind of shell. It is accessible via serial port and maintenance cable. It has an ability to run signed binaries, list and dump contents of the file system, upload new files to the pin pad, and some other commands. It is very useful, but we still don't have an ability to run our unsigned code. As a result, we can upload any files, execute signed binaries, modify configuration of the device, but we are still limited by digital signature checks. In this case, we already have extended user input from the merchant application to some internal commands. Once a merchant application is limited to the encrypted TMS server interaction and varies from bank to bank, let's focus to vendor-specific issues. We need to look what can we do with some shell commands. When we tried to fuzz user input for some commands, we've got a crash. We passed too many symbols to shell command and we got classic buffer overflow. Also useful thing is in this crash is output on the display. We can see crash addresses and some register contents. As you may be noticed, 13 in hex in the least significant bit of CPSR register means that we got a crash in supervisor mode. It equals to the crash in VerixV operating system kernel. The investigation of this crash points us to buffer overflow in Verix operating system call. As you can see on the pseudocode, there is a classical memory copy mistake on the stack. Additionally, it is needed to be said that there is no measures turned on in order to prevent code execution. Finally, we have got the code execution on any Verix device, because they all have the same code base. But another interesting thing is the case in the boot chain. Every vendor reinvented their own boot order in the case of pin pad devices. Sometimes the boot order chain is very long. It also has a lot of legacy because almost all of these operating systems developed before traditional secure boot approach became a mainstream. After reset, the zero-stage bootloader should be started. Usually it is located inside MCU in form of mask ROM. It loads the next step bootloader from flash memory and checks its cryptographic signature using the key stored in OTP ROM and any other secure memory. Every next bootloader also should check the cryptographic signature of every loaded piece of code, etc., etc. Finally, when operating system loads an application, it also should check its signature. Now you see the Verix operating system terminal bootlog output. Internally, it is called SBI. As you may see, it can work with USB sticks, and in this case, it loads Verix operating system kernel. Please look at the operating system kernel output. Here you can see the Broadcom CPU model that was previously rebranded to internal Verifone name. This bootloader is located at the start of NAND flash memory. The purpose of interaction with USB flash is factory restore. If USB stick is recognized, it goes to look for signed script file that executes a sequence of actions to burn new operating system kernel, for example. Another interesting ability of this script is to put the bootloader to low-level command line interface. However, we don't have any examples of signed scripts. When we had a look into bootloader, we found some protocol handler. If we dive deeper, we faced with the same protocol as used in usual maintenance for terminal loading. The utility for this protocol is called DDL and can be found in the internet. And finally, there is another classic memory copy related bug was found. The weak logic is contained in the update format parser and allowed us to write any memory regions without any restrictions. The most fast way to exploit this vulnerability is to call restricted part of bootloader. As we have mentioned before, there is very useful command line interface parser, and now we are able to call it. As you can see, this command line interface prompt called without valid signet script file. This mode allows us to access the whole file system, to dump and burn any regions of flash memory, to load any code into memory and pass execution to it. As a result, this pin pad can be exploited using the physical connection before operating system is loaded. The last case is Linux-based MX series Verifone. This is one of most recent pin pad model, and it is also PCI certified. It has advanced permission settings like supervisor, user and maintenance modes. Also, the root user isn't allowed to get access to different files on the pin pad file system during to role-based access control settings. We have already seen the research related to these models at DEFCON 25 3 years ago. The MX series of Verifone pin pads already were hacked, but in some reasons we have seen exactly the same problems on our projects with the latest firmwares. The exploitation chain is default password for system mode, command injection in maintenance mode, privilege escalation based on vendor service, and finally race condition in role-based access control configuration. This presentation describes all the steps how to get into this model, but this is not the end of a story about MX series. In the bootlog we see the same chip, what already known as BCM5892, surprisingly faced with the same bootloader as in VerixV pin pads. But in this case it loads not the proprietary kernel model, it loads U-boot. Finally, it has literally the same code and can be exploited in the same way before operating system is loaded. That's almost all about technical parts of terminal weaponizing, and I am going to pass our virtual floor to Timur.
So now let's try and determine rules of this POSWorld. So I think rule number one is that if PCI console doesn't require any specific thing, you probably won't find them in modern point-of-sale terminals. For example, PCI console doesn't say that firmware should be deleted during tamper protection, and they never delete a major piece of firmware, mostly just encryption keys. And even with encryption keys, PCI doesn't specify how exactly these keys should be deleted, wiped in most secure way, and that's why every vendor decides to do their own implementation of deleting keys, and many more discrepancies you can find in different vendors. So rule number two, I guess, is that for many years vendors are trying to do proprietary everything. They did proprietary operating system, specific custom outputs, physical outputs, proprietary protocols. They had a lot of special modes and kill switches which allowed them to get access to maintenance and so on and so on. And as you can see, that didn't bring them to a very good end in the end. So proprietary software is not the best way to maintain security. It's quite interesting to look at what can and can't be done with two groups of devices. You see, on Verifone you don't have dedicated chip for cryptography, where Ingenico actually has a specific chip where all cryptographic features, functions are executed. And the only one difference is that you can't actually clone terminals, Ingenico terminals, and you can't keep the persistency after rebooting, so each time you need to compromise device once it's been turned on and off. However, you still are able to clone cards, clone pin codes, and track to data. So how is this possible if device use a dedicated chip for encryption which can't be compromised? You see, if you will think about that, you would assume that once pin code is entered on a pin pad, information is sent directly to that dedicated chip where it has been encrypted, sent to the main application, and then it will be sent over the internet to the issuing and acquiring bank. However, in fact, it's not that. In fact, information from the pin pad is sent to the main application, and only after that main application communicate with a dedicated chip, so pin code will be encrypted and then sent over the internet already encrypted, because that's the main goal, to protect data, to protect cardholder details from being intercepted over the Ethernet, over the internet, not on the point of sale terminal. And as you can imagine, if hackers will be able to maintain and run a specific malware which will be looking in the memory and collect pin codes or track to data, this information can be stolen before it will be encrypted. Therefore, this protection is not as good as you would have expected. Now, to make a fully functional clone of the terminal, you need to steal or extract a few different encryption keys. So it should be key for network encryption, for encrypting the PIN, message authentication code, keys, and so on and so on. But once you've done it, you will be able to create a functional clone of a terminal which can be used to facilitate more fraud. You can read more about that in our white paper on our website. Initially, when we started this project, it came from the bank, who said to us, hey, what hackers can do with compromised terminals? Can they facilitate fraud? Can they do some fraudulent transactions we won't be able to expect? And this is how this research started, and we actually proved to the bank that once you compromise the device, you can do a lot of things with cards, stolen data, and do a lot of unauthorized transactions, which can't be done in normal circumstances. We actually even made a separate research on that topic. It's available on paymentvillage.org. You can read about that. So it's basically about how transactions can be done, purchases without knowing PIN, and how this affects modern requirements of PSD2 legislation about contactless transactions. So a lot of questions remain at this point. For example, we still are not sure how many devices are on the market and are still vulnerable, because each device should be updated almost manually. And for example, Ingenico never presented any updates to us, so we don't even know how secure they are. Also, we don't know, is it actually possible to downgrade firmware on Ingenico or Verifone point of sales, because we, for example, still have vulnerable firmwares, and as you can imagine, downgrade attacks are quite popular for different type of firmware. So I would like to say thanks to all of our team. This work would not be done without them, so thank you so much. If you have any questions, you can reach us out, Twitter, email, or send a form on paymentvillage.org. So thank you, thanks everyone.